This video is to present the executive summary of the effective manufacturing system of TRINITY and Mentec to use operator stress for optimized productivity and employee satisfaction. The presented solution is developed in TRINITY Demonstration Program 1, a program to improve the agility of European SMEs in the manufacturing industry. Mentec and TRINITY developed a cobot-assisted effective manufacturing system for complex assembly tasks. Stress detection was integrated to measure the operator's emotional state during the cobot-assisted assembly task for optimal operator engagement, both in terms of operator well-being and productivity. The demonstration includes a showcase in which human factors are included in the execution of an assembly process for optimized production, eventually opening the gateway for effective cobots. The companies TRINITY and Mentec are located in the vibrant heart of Brainport, Eindhoven. Brainport represents a rich ecosystem of OEM companies, innovative suppliers, and R&D institutions focused on solutions for the high-tech manufacturing industry with major players such as Philips, VDL, and ASML. Mentec commercializes emotion artificial intelligence platforms based on wearables for physiology and speech recognition, behavior models and machine learning to facilitate behavioral change, to improve self-management, to enhance quality of life and happiness. One of their products, the Hume, is an early warning system for stress detection initially developed to provide a voice to the vulnerable people with intellectual disabilities. TRINITY is a machine builder and system integrator. We improve the production performance of our high-tech customers, leading to lower production costs, higher production quality, and flexibility by providing a unique combination of competence in engineering, production and assembly techniques, and automation, and application of knowledge in joining and bonding. Products include robotics-based assembly systems, bonding systems for manufacturing of high-precision, high-quality products, and engineering services. The objective of the project is to demonstrate a smart factory concept for robotics-based manufacturing of complex photonics products with inline operator stress detection and safety and optimized production in terms of yield and product quality. This demonstration is based on a modular machine platform with robotics functionalities for efficient and customized production of complex photonic systems. The platform has inline monitoring and quality control functionalities for inline adaptation of production steps. This demonstration includes an appealing showcase in which the stress level was successfully included in the execution of a manufacturing process for optimized production, eventually opening the gateway for effective cobots. Mentec and TRINITY demonstrated an effective production platform for high-quality production of low-volume, high-mix products. The demonstrations included a pick-to-light assembly unit assisted with a cobot, the Hume stress detection platform with wearables and trained models, and optionally, a camera system, a dashboard to visualize the production and stress parameters. The project partners also demonstrated the impact of effective manufacturing, in which stress detection was integrated to measure operator stress during cobot-assisted assembly tasks for operator engagement, well-being, and productivity. The main results of the demonstration of the effective manufacturing system, or AMS in short, included the successful demonstration of the platform. The platform integrates a cobot-assisted pick-to-light system for assembly of complex photonic products, a stress detection module for operator stress, and a dashboard to visualize correlations between the process performance and operator alertness. The project also demonstrated the influence of operator alertness on task performance. The target and achieved key performance indicators are listed in this table. The indicators included a number of dissemination events such as presentations and pitches, business development targets such as new contacts and collaborations, and machine performance indicators. In general, the demonstration project appeared to be successful in achieving both the business and the technology performance targets. A typical result of stress-related performance is indicated in this figure. 20 test operators executed a number of assembly tasks in which the operator's stress was measured both with sensors and with self-annotation according to SAM labels, and the productivity was measured as expressed by the OEE value. 3 conditions were tested: a situation without stressors and time pressure, a situation with time pressure, a situation with annoying stressors to increase the pressure. The results clearly indicate the experimental design indeed led to an increase in both alertness and negativity. The output performance of the assembly task dropped from 100% to 58%. A typical result of the perception of losing control in cobot-assisted assembly is demonstrated in this figure. In total, 10 test operators executed a number of assembly tasks in which the perceived control of the operator was measured with a scoring table. 5 conditions were tested. Test 5 represents the control situation without cobot. Test 1 represents a situation in which the operator had control via a button, cobot worked efficiently, and reacted promptly to the operator's command. Test 3 represents a situation in which the operator had control via a button, but the cobot worked inefficiently and reacted with a delay. Test 2 represents a situation in which the operator had no influence on the cobot worked efficiently and reacted with a delay to the operator's command. Test 4 represents a situation of no control, no button, and a delay. The Affective manufacturing system integrates a novel operator stress detection module based on measured physiological features of the operator and an artificial intelligence algorithm for stress detection. Production performance and related operator stress is displayed on an interactive dashboard used for both stress management and process control. The measured stress levels are used in a dashboard that displays the relevant decision factors such as the stress indications or emotional state of the individual operators as determined by the measured and analyzed features, information about the circumstances such as privacy and work condition of the employee, information about the production process such as the measured performance indicators of product quality, productivity, failure, etc., production instructions such as the complexity of the instruction or work. Possible scenarios to use the outcome of stress detection is displayed in a decision tree with intervention on the human and machine level. The operator is activated in case of under-alertness such as drowsiness. This can be done with environmental influences such as music, voice, or light, or by direct instruction. The operator is urged to take a break in case of undesired stress development. The operator can be relieved. The cobot can overtake certain assembly tasks, both complex and easy, to influence the operator's performance. The product order and assembly instructions can be changed to meet the operator's demands with respect to stress and perception. The Trinity project support was instrumental for delivering the demonstration. It provided a strong learning network on Agile, robotics-assisted manufacturing. It also provided reflection on the merits of effective manufacturing. The Trinity project provided a platform to present the concept and impact of effective manufacturing, for instance, presentations on conferences. Finally, the Trinity project supported the realization of the demonstration in terms of advice and knowledge. The purpose of this use case is to illustrate the benefits of incorporating the operator stress in cobot-assisted manufacturing, both from productivity and operator happiness. A focused and complementary consortium with collaborators from different industries such as Mentec, TGEMA, ABB, and TU Eindhoven facilitated the development of the demonstrator. For more info on this use case, please see the Trinity catalog. More information about the demonstration can be obtained from Erwin Meinders from Mentec or Dan Linnaerts from TGEMA.